2, 1. All right, so welcome in. So an application of Bernoulli's equation. So here's Bernoulli's equation right there. Now, if you want to know kind of assumptions, kind of how this term comes about, I'll put up a link up above there. So I'm not going to talk about Bernoulli's equation here. I'm just assuming that you are familiar with it and now you want to be able to apply it to an example. All right, so that's what you have there. Now, the example that we're given in here is that we actually have a fluid, and this particular fluid in here, so notice that it's water, so that would be the density. Now recall, okay, so density would have been really, okay, so for water, just times 10 to the 3, and that would have been the density, which is in kilograms per meter cubed. Okay, so if we're going to need it, so that's what that would be. You typically will assume that it's just 1,000. Now, if we have this water and it is flowing through, so maybe this is some kind of a hose which then narrows down, and it looks like we want to be able to find out what the speed at the exit point is. So let's take a look and see. And we're going to be applying Bernoulli's equation in order to solve this. So in Bernoulli's equation, we always know that the three terms between the pressure, between the actual speed, which is kind of the kinetic energy component, and then the kind of potential energy component related to the height of the fluid. So those three terms are always equal to a constant, which means that those three terms at the bottom here are going to be equal to the same three terms up above. So if you would write it out, this is exactly what you would have. So this is on the left-hand side, the bottom, okay, of the fluid, which is at a certain pressure, at a certain speed, and a particular height with respect to a reference. And then this on the right-hand side would be your pressure, okay, and then the speed and the height at the exit point here that we want. Now, at the exit points, this is something that you should know, so as a student or a learner, is that whenever you are asked about anything about an exit point at the nozzle, unless they tell you otherwise, pretty much it's going to be at the atmospheric pressure. Now, I'm going to make the assumption here, so notice atmospheric pressure is 101 kilopascals, or 101,325 pascals. And, you know, your teachers can give you exactly what they want to use. Sometimes we round this off. I'm going to just use this number for the pressure at the nozzle. And that is very common, okay, because that pressure has to be the same as it is on the outside. So within here, if I start substituting all of these components in here, so at the bottom, you know, let me maybe kind of use the red pen here. So let's substitute everything in. I do have, it looks like everything is in metric standard SI units, and you can always double check. So notice newtons per meter squared, so that's pascals. Speed is meters per second, the height is in meters, and you have the same thing on the right hand side. So notice meters here, pascals for pressure, and of course we're looking for the speed. So let's dive into this. So this is just basically now math and substituting this in. So I'm going to drop the units. I'm going to have 1/2. This is the density that I have in here. So my density is water, so I'll put it at 1,000. The speed itself, so in this case it's 11, this is going to be squared. And then finally plus, you know, so here's the density in here. And then this is going to be times gravity. So the gravity is 9.8 meters per second squared. And this is the height, which is going to be 2. All right, so that's the left-hand side that you have. Now, all of this is supposed to be equal to, now notice the right-hand side. So on the right-hand side, I have 101,325. So that's the pressure, the atmospheric pressure on the outside. This is going to be 1/2. Okay, notice this is the density, okay, of times the speed, okay, of that exit point. So that's going to be the exit point over here, right? So that we have. So that's going to be what we're trying to find out in here. And that finally is going to get added up, okay, to the, so this is going to be density multiplied by 9.8, and then this is going to be times, this is at 20 meters all the way up above there. All right, so let's do that. So there's only really one item that is missing in this entire thing, right? So there is really no items, okay, associated with anything else. All right, so let me just do all the calculations. I'll do that in fast forward fashion, okay, and I'll be right back. All right, so I simplified it a little bit. So the left-hand side, so here it is, okay, so that's what we're going to have on the left-hand side. Here's on the right-hand side, okay, so we have this particular term, so this is just this added plus this, okay, so that's what we're going to have over there. And then finally, okay, so this is the last one, so half of 1,000 is 500, and that's what we have. Okay, so I can move this over on the other side, and then I can divide by 500, okay, in order to get it. So let me continue with this. All right, so and there we have it. Okay, so this is what we have right there. And now we're just gonna take that answer, so divided by 500, so that's what you see there on the calculator. And now I wanna take the square root of this. Okay, so I'm gonna take that answer, okay, and then take the square root of this entire thing. And there's my answer. So I just rounded to 3 significant figures for this, so it didn't really specify. Okay, so within here, so if you wanted to, you can round to whatever you feel confident in. And that would have been the actual speed. Notice how much faster it has to be than the actual bottom one. So to maintain, because you have a pressure drop of quite a bit. You also, the height is kind of going upwards as well. So, there's going to be a much different speed. So this is almost 100 meters per second. So it really is torpedoing out of there, So if you're thinking about kilometers per hour, so this is, approximately close to 360, kilometers an hour, which is pretty quick, in terms of the nozzle. So that's an application that you have, where the heights, are now all of a sudden different. And if they are different, then we can't actually no longer use Bernoulli's principle. We have to use the full Bernoulli's equation in order to solve it. All right, so thanks for watching, and we'll see you in a future video. Bye, everybody.